Hello everyone. I honestly expected this introduction to take the organizers a little bit longer, so I'm not fully mentally prepared, but nonetheless. Hello, as aforementioned, my name is Jakub Trąd. It's nice to be here, especially given the fact that I actually used to work here 3 years ago. And it's been nice, except for the entire pandemic stuff that happened around the time. Today I want to give you a talk about Merkle Trees. The title of the presentation is How are Merkle Trees? Because I wanted to do a little bit of a joke, like, oh, you know, everybody always asks, what is a Merkle tree? Like, how do I use it? But nobody ever asks, how is a Merkle tree? But by the time I actually started writing this presentation and realized that this joke is not that funny, I couldn't be really bothered to contact the organizers and change the title. So here we are. But the reality of this presentation is that it's what are Merkle trees, obviously, and how do we implement them in Rust. In this presentation has like two sections. The first will be a small visual theoretical introduction to like how a Merkle tree works, how do we construct it, how do we make use of two interesting properties of it. And the second part of this presentation is a semi-live coding implementation session. What's in it for you? Well, at the end of this, I mean, I could say it now actually. I was technically given permission by my supervisor to say that, hey, we're hiring at my blockchain company. So if you're not blockchain averse, you might be interested in learning that a lot of companies will use like a Merkle tree assignment as their recruitment task. This has happened to me twice, for example. So if you learn about Merkle trees, you're quite a bit ahead of the curve against the competition. So without further ado, let's jump into like what is a Merkle tree? It's a tree, as the name implies. We start with a set of leaves at the very bottom, right? Because that's how software engineers imagine trees growing downwards. The bottom set of leaves, right? It could be anything. It could be files, could be abstract user data, could be directories. It could be anything you really want. But for the purpose of a Merkle tree, what ends up in the leaf is actually just a hash of whatever you're actually using, right? So it could be a hash of a file, a hash of a directory, a hash of a website in the index you have somewhere or something like this. Then we take these leaves in pairs and we hash them going up. So we hash the first pair, second pair, third, and so forth until we arrive at a number of hashes, same as the number of leaves divided by 2. We do this multiple times until we finally arrived at the root of a Merkle tree, which is a singular hash that represents, as hash properties give you a certain uniqueness and consistency of the data you have. Applications of Merkle trees range from, like, let's face it, probably if you are learning about the Merkle tree, if you're using a Merkle tree, chances are high you're either working in blockchain or you're interested in working in blockchain. However, during a brief research for this presentation, I also learned that apparently AWS's DynamoDB uses Merkle trees for consistency checking, and this is probably very contentious, but I found an article which explains that Git version control system uses Merkle trees internally to like produce efficient deltas of the data that you wanna check that you have the right ones. Even though I'm pretty sure they don't actually call it a Merkle tree in the implementation. But I just think Merkle trees are cool. And you might be wondering right now, how is this different from just concatenating all the data I have and hashing it together, right? For the purpose of consistency checking or verifying that, I have all the right data. As it said, say you don't know that 500 files, you could just hash them together, right? Well, Merkle trees give us two important properties, and the first one are inclusion proofs. Inclusion proofs allow us to verify efficiently that a certain leaf is indeed, or actually maybe let's rephrase it a little differently, contributes to the root hash of the tree. So for example, if we have here the leaf number 4, do you guys see it, by the way? Is it visible enough? Leaf number 4, and we want to verify efficiently to somebody else, to ourselves, however, that it is indeed part of the set. Well, let's build it from the bottom up. So first, we calculate the hash H2, of which L4 is a part. For that, we need to provide the sibling L3. Then to hash H5, we don't need L1 and L2, we only need to provide H1. And then finally, to calculate H7, we only need to provide H6. So we skip, L5, L6, all the way to the end of the tree. All the data highlighted here is what we would call a Merkle proof. And you'll notice, and this will be important in the later part of the presentation, is that this Merkle proof, apart from just containing the data itself, so like these nodes all the way up the tree, or through like a path to the root, it also has a certain sense of directionality, right? Like we need to not only say that our sibling was L3, we need to say our sibling on the left side, on the left with respect to our parent, right? On the left of the branch was our sibling, and H1 was also on the left, but H6 was on the right. Another property of Merkle trees is that they allow us to efficiently update the entire set, right? If we were to say have 500 files with 1 terabyte data total, and you want to hash it all together, one file changes, you have to hash it all again. That's expensive. With a Merkle tree instead, even though we do have to store double the data in terms of hashes, right, which will become apparent later, when we actually update the hash, the only thing that changes is the path all the way to the root of the tree. So for example, we updated L4 to Q4, we only update the hash above it, and the root of the tree. But here's me talking about efficiency. How efficient is it really? Before I give you like the big O notation, I want to talk about measuring the tree. So how do we describe a tree? A tree is typically defined by its depth, and perhaps at this point it would be, I should have probably prefaced this before I started the presentation, but I'm not a cryptographer, right? I'm just a lowly Rust software engineer. I just think Merkle trees are cool. So take anything I say with a grain of salt. I might be wrong here and there on like naming conventions or such. But what we're talking about here is technically a sparse binary Merkle tree. Binary meaning it splits into twos, and sparse meaning we have empty nodes which will be allocated to 0. You'll see that later. A depth of the tree is isn't typically how many rows of nodes we have. It is instead how many gaps between the rows we have. So the Merkle tree in the picture is of depth 3, right? And a tree of depth 0 is useless. It's just a single hash. It has 1 leaf and 1 node. A tree of depth 1 has 2 leaves and 1 root hash and 3 nodes in total. A tree of depth 2 has 4 leaves, 7 nodes. You might be seeing where it goes. A generic tree has 2 to the power of depth leaves and 2 to the power of depth plus 1 minus 1 nodes. I skipped the slide. Okay. So how efficient is an update? Well, we only need to update, in reality, depth plus 1 node, right? So if we do an update on Q4, we only need to update, this is a tree of depth 3, right? We only update Q4, H2, H5, and H7, giving us a total 3 plus 1, depth plus 1 nodes. Now you can, I don't have a proof that this is generic in every case for every depth, but I think it stands to reason, right? Let's take a tree of depth 20. A I actually didn't double check these numbers, so they may be a bit off, but with a tree of depth 20, we have a little under 1 million leaves and 2 million nodes. Actually, this is definitely wrong. This should have been 1 million. We have a little over 1 million leaves and a little over 2 million nodes, right? But when we do an update of a single item, we only need to update 21. That's logarithmic efficiency on an update. How efficient is an inclusion proof? Same deal. We have a tree of depth 3, and now, depending on how you want to structure your verification check, maybe you have this H7 hash provided somewhere externally, maybe you store it, maybe you provide L4 externally, but in general, it's also going to be logarithmic in terms of memory efficiency for inclusion proofs. Okay, so far so good? Are you guys with me? Are you with me? For implementation, we're Rust developers here, and Rust developers love thinking about memory. So let's talk about memory layout. We have a tree. Let's color the nodes in a totally arbitrary scheme. An initial solution might be to store the tree in a breadth-first manner. So we have the root of the tree in the 0th position in our buffer, the first and second children in the 2nd and 3rd position in the buffer, and so on and so forth, giving us this indexing scheme. However, I know something that you don't, which is that it will pay off greatly if we skip the first node in this buffer and use one-based indexing scheme. For reasons that will become apparent during the next slide, which is index calculus. Now that we have our tree stored in memory in a linear buffer, it would be useful to be able to still operate on it as if it was a tree, right? So we want to ask questions like, what is the parent of node at index 6? What is the leftmost child of the node at index 5? What is the sibling of node 2? And so on and so forth. So what is the index of a parent? Any thoughts, any ideas? Yeah, exactly. It's floor of index divided by 2. Index of sibling, I want you to pay attention to evenness and oddness of the numbers here. Do you see a pattern? If the given index is even, then my sibling is my index plus 1. Otherwise, it's minus 1, right? You can see it clearly here. 4 is even, my sibling is 4 plus 1, 5. 5 is odd, my sibling is 5 minus 1, 4. By the way, if we didn't apply this trick of skipping the first root, for example, the index of a parent is now I plus 1 over 2 minus 1, right? And for index of sibling, this gets just flipped, but then we have the next one, which is depth at index. We also want to know which level a given index is on, right? Here on the top, you have the index of the node in the tree, and below it is the depth. And I want you to pay attention to the leftmost side of the tree, so the leftmost branch. Do you see a relation between the index of the tree and its depth? It's a logarithm, a floor of a logarithm of base of 2, right? Because given that the next level starts with the next power of 2, it stands to reason that all the indices in this level, when logarithmed, will give you a power of 2 plus some decimal points. We also need to think of the children. So what is a child at a given index? What is a child at index 3? And what is the left child at index 3? And what is the child, right child at index 5, for example? We know previously that to get a parent, we divide it by 2. So it should be pretty obvious. I mean, I did this presentation before, so I know it, right? That it's going to be times 2 or times 2 plus 1. Awesome. With that out of the way, let's get down to the implementation. And as I said, this is going to be a semi-live coding. I have a little scaffolding project set up, and I implemented all of the index calculus equations that we just talked about. So we have index of parent, index of sibling, depth of things, etc., etc., etc. Because it's frankly quite easy to implement. And we're going to implement our Merkle tree. Can you, by the way, is the font okay? Should it be larger, smaller, color too bright? All right. For our hashing functions, we're going to use SHA-3, the 32-bit variant. And I prepared a set of tests for us, right? First, we're going to want to be able to implement a tree with an arbitrary initial leaf value and make sure that for a given depth, it initializes with an expected root value at the top. I have these values from like a battle tested library we use at work. So I have high confidence that these are correct. Next up, we want to be able to update a leaf and have this change propagate all the way to the root. This is trivially testable on a small tree, right? We have an initial value for all the leaves set to all zeros. We initialize tree of depth 2. So you will recall that a tree of depth 2 has 3 levels of nodes. We'll update the first leaf to a new value of all ones. Therefore, like you can walk through it without actually implementing the tree, that we expect the root hash to be equal to a hash of the new value and 0 and a hash of a 0 and 0. After we're done with updating, we'll need to update proof generation. Before actually going to proof verification, we'll go first to proof creation. So the first test will give us a proof for the first leaf in the tree, and this is the graphical representation of that. For the first leaf of the tree, what we expect to be in the proof is that the sibling on the first level is on the right side, and its value will be 0, right? Because that's the initial value we'll be using. And the sibling on the second level will also be on the right side, and its value will be hash of two leaves all set to 0.
Could you expand a bit more on what a proof here is? Like what it...
Yeah, a proof allows us to verify that a given leaf contributes to the root in an efficient manner using only O log n items, right? Like say you want to send it across a network or store it in a database or something.
Probably efficient, but the non-type proof system do not need to know anything about other members.
Well, they do.
Only about one of them, and you can.
Yeah. I mean, in order to create a proof for yourself, you need probably the entire tree. Yes. But on the verification side, you only need the proof, right? And the root and the proven value and the logarithmic size of the proof. Does this answer your question? Okay. It's better. So that was the proof of the first leaf. Then we have the proof of the last leaf. So again, the situation will be flipped. We'll have the sibling on the left side set to 0. And then on the second level, sibling on the left side again, set to a hash of 2 0 values. An arbitrary proof set somewhere in the middle. We have a tree here again of depth 2. We create some arbitrary leaf values. We update them accordingly in the tree. So we have a tree which contains 0, 1, 2, and 3. And then we get a proof in the middle. So we should see that on the first level, our sibling is on the right side, and on the second level, our sibling is on the left side, and all the hashes are what we expect it to be. And final test, after the implementation is done and correct, is the verification of the proof. A typical API for inclusion-proof verification of Merkle trees is such that you don't, it's not a function that like throws an error or gives you a Boolean. It's instead a function that accepts the proof, which are all the sibling and their, sides, directionality, if you would. It also accepts the value you're trying to prove the inclusion of, and it returns to you the root of the tree that this proof verifies to. So then you can grab it, compare it against the root you actually have stored somewhere, and be sure that it's correct. Okay, any questions?
Why do we use trees and not instead a hash set? It gives us still, it gives us even better kind of lookup and vision, but it doesn't give us this ordering of the nodes that you mentioned. For example, we would add our L4 from our initial example, and we could check if it's present in the set.
But you have to, But that's the thing is that you have to have a set, right?
Right.
Where with a tree, for example, you might, this is like a blockchain thing, right? Typically, when you say, okay, not a terrible fan of NFTs, but a thing about NFTs is sometimes what they did, right? They wanted to have a initial whitelist of addresses that are allowed to mint ahead of everybody else, right? You could store an array of or a hash set of all the addresses in your smart contract, but storing data in a smart contract is very expensive. So instead, you store only the root of this Merkle tree. You host the Merkle tree somewhere off-chain, and then when somebody wants to verify that they can mint, they just give you the proof, and you're proving that their address is indeed contained with the proof against the root of the tree.
Okay.
Yeah.
Take into consideration the fact that we don't have, like, it's in a distributed context.
Yeah.
Right? So
Well, it could be, but yeah. All right. Let's move on to the implementation then. First up, we're going to want to initialize our tree with a given initial leaf value, calculate all the roots, all the hashes all the way to the top, and make sure it's correct. Firstly, as I mentioned before, in our indexing scheme, the root of the tree is actually index 1. So let's just return that here. And let's move on with implementing our tree. We'll obviously need a set, a vector of nodes, which have initial leaf value. And we have a function already prepared, which gives us the number of nodes for a given depth. Now this function, you might remember previously in the presentation, I gave you this equation with the -1 here, but you'll know that since we're skipping the index, it's actually to the depth plus 1. It all comes together. It's truly beautiful. So that's how many nodes we'll have in this vector. How do we initialize all the hashes inside it? The rightmost, the rightmost, I don't think that was correct, by the way, but the rightmost part of the hashes is already initialized, right? So we need to only initialize the second level, third level, and the root of the tree. Let's start off with a recursive implementation. In this recursive implementation, we will start at the top and recursively hash the children at the bottom level all the way until we get to the actual bottom of the tree. And then, through the magic of recursion, we end up back on top. What will be our exit condition from this recursive function? The answer is actually quite simple, which is that if our left child is outside of this buffer, right? So we get the left child at this given index, and we can compare it against the number of nodes we have allocated, right? So if it's outside of that, we know we've reached the end of the tree. And we, sorry?
Yeah, I was wondering.
Yeah. Otherwise, we'll get also the right child. Thank you, Copilot. And hash recursively. Oh, sorry, I forgot to mention, I suppose, that there is a concatenation function here already prepared, which grabs the two hashes together, concatenates them together, and gives us the resulting hash of that. So we hash recursively the left child, we hash recursively the right child, and we set nodes at our index to be a concatenation of the nodes of left child and nodes of right child. All right. And we have to recursively hash starting from the root of the tree. In the tests, and fun fact, if you're not familiar with the syntax, this comes from the test case crate, which has been developed in this very company by a member, by an employee who no longer also works here, but I highly recommend it. You'll notice that we have a depth of 5, 7, and 20. You might recall that for depth of 20, we have a little over 2 million nodes. So we have to hash half of that. So that's 1 million hashes, right? And you'll notice that it's a bit slow. Does it have to be?
When you construct the string, right?
Yes.
From the start.
From the start, from initial value. It doesn't have to be like that. There must be a better way. Sorry? I have here, yeah, so we have a little over 1 million hashes to do, but we don't have to live like this, okay? You'll notice that all the initial leaves are set to the same value, right? So all the hashes on the second level are the same. All the hashes on the third level are the same, right? In reality, we only need to do how many hashes? Depth hashes. Depth number of hashes, or give or take plus minus 1, right? So let's do that instead. We'll abandon the recursive approach, although I suppose you could do like a memoization here to do that instead, but I prefer this, which is we'll calculate the initial value at given depth. Initially value, and this has to be depth plus 1 because you'll recall depth actually refers to the number of gaps between the rows, so we'll need plus 1, right? Then to calculate these initial hashes, we want to go from like starting at the second to last value and hash it using the last value, and then step backwards, right? So we're going to go for I in 0 to depth reverse. And we're going to say initial value at depth I is equal to, oh yeah, thank you, Copilot, exactly that. Now, instead of hashing recursively, we can simply go through all the nodes in the tree. Get the depth. And set the appropriate value using initial value at depth. And if I didn't make any mistake here, it should be vastly faster. All right. 15 minutes to go. I think our time is good. Next up, we have the set function. The set function should update a leaf in the bottommost row, right? And then propagate this update all the way to the top of the tree, resulting in the root change, right? I'm also going to do a recursive implementation here, but you'll notice here one thing is that this function accepts a leaf index, right? It's not an index into like this node structure, so we have to convert it first. And we're going to use again the fact that I think I'm mentioning ad nausea right now is that the number of nodes is 2 times the number of leaves. Therefore, we just need to offset by the half of the length of all the nodes that we have. So our index is just not 3, like that. In order to update the tree itself, we're again going to go with a recursive approach. This time we're going to go bottom to top. So we're going to update let's just start writing this because I think it ends up being a bit funny. In a morbid way, which is that we'll go all the way to the top until we don't have a parent, right? It's gonna be if, actually, let's use the hot off the press. And if we have a parent, we're gonna get our sibling. We also need to know whether or not we are the right sibling. So simply check that we are, sorry, this is wrong, is left. That our index modulo 2 is indeed 0. And if we are on the left-hand side, we update node of the parent to be equal to that of a concatenation of the newly updated value. And what? Oh, it's an option. And the sibling on the right-hand side, otherwise the sibling will be on the left-hand side. And we do so all the way until we end up being a node without a parent. Set recursively nodes parent. So first we'll update the actual value that we want to update, call set recursively. And if I didn't make a mistake, then I think this should work. It does indeed. The function is, the test is not aptly named setRoot, but should be probably update the tree, but it works nonetheless. Is everything clear so far?
On what basis do you choose the index of the leaf to place the whole column?
What do you mean?
How do you know if the leaf is free to be used?
Well, I update an arbitrary index, right? It is up to the user of the Merkle tree to choose how they want to store it, right? For example, maybe you store in the Merkle tree the addresses of some wallets that you want to be included in a whitelist of some sorts, right? So then you will also need to store some index for yourself that will let you know, hey, the next free index is this, right? Or maybe you just go by which values are set to 0 at that time. By the way, something that I didn't mention, I mentioned that this is a technically sparse binary Merkle tree. It's sparse because it also provides an additional feature of proving non-inclusion, right? Not only can we prove that a certain value is present in the tree, we can also verify that it is not present in the tree because all the initial leaves are set to 0.
But for proving, you also need to provide an index, right? Which you want to prove.
Funny thing, kinda yes, kinda not. So you don't need to provide an index. You just need to provide the leaf value and all its siblings all the way to the top, right? But, and I started making a graphic for that, but I had abandoned it because I thought it would be too esoteric knowledge. there is a certain interpretation of an binary representation of an index of a tree that it is also its path in the tree. Let me try and explain it without a visual aid. If you take 4, so 1, 0, 0, the 0 means we go to the right, 0 again we go to the right, right? And the same will be true for 7, right? 7 will be 1, 1, 1, so we go left, left. 5 will be, hold on, I have, 1, 1, 0, 1. 1, 0, 1, so we go left and right.
It's basically a binary color.
Yeah, and so that's kind of what I'm getting at your question, is that you don't need to provide an index, but by virtue of providing the directions in the path, that can be decoded into an index.
Okay, but well, it doesn't solve anything, because you must know the location of the leaf which you want to check.
If you want to get
location, either it's an index,
yes,
or this.
If you want to get the proof, yes, but if you already have the proof, you don't need it.
Okay.
Yeah.
Mm-hmm. Yeah.
All right. And we're gonna get to it, and I hope just now for the proving part of this. First set of tests, there are 2 tests. We just create, or is it 3 tests, which create proofs and ascertain a structure of them. So let's do that. For a given leaf index, what we need to do is we need to grab our sibling, take its hash value, take the Boolean that represents whether or not it's right on the left or right side, go to our parent, take its sibling, take the directionality, all the way to the top until we no longer have a parent, right? So again, a recursive implementation which is going to work like this. We'll have a vector containing proofs, which we're going to return. And again, we accept the leaf index, so we must convert it to an actual index. Right? Proof recursive accepts a proof, which is a mutable vector of a Boolean and a hash. We also need access to the list of all the nodes. And we need the index, which we're proving right now. So let some, no. Do you guys also find yourself using the let else syntax all the time? I can't stop using it, it's so good. We'll take the sibling, we'll see if we're on the right hand side or not. That's the other way around. And proof push is left and nodes of sibling. And and just do that recursively for our parent index. And if I didn't make any mistakes, this should now work for the proof set of tests. It does indeed. If you want, we can go to these proofs again. So you'll note that for a Merkle tree of depth 2, which is exactly this situation, we set some initial value of all zeros for all the leaves. When we modify, sorry, we don't modify anything. Then we just get the proof at the first index, right? So in the proof, we expect it to be the right-hand side sibling. So the first Boolean is true. And this value will be initial value for a leaf, so all zeros, right? Then the next sibling is again true because it's on the right-hand side. And its value is a concatenation of all zero hashes, quote unquote. Same situation occurs with proof of last leaf and arbitrary proof. All good? All right. Final test, final thing we have to implement is proof verification, which just so happens to be extremely simple, as you'll just see. We'll need to return a number of nodes because that's what my test requires. And you'll notice that this verify function is not, how do you call these in Rust, like a method of a struct, right? It's a free floating function associated to this type because it doesn't actually need the access to the node, right? All we need is the proof, the leaf value we're trying to prove, and we want to return the root that we expect. So we're just going to go through the proof, grabbing each value along the way, hashing it together, and we should arrive at the root of the tree as expected. Oops. Yeah. Is that correct? Is on the left-hand side. Therefore, our hash is on the left, sibling is on the right. Yeah. That should verify against the expected root of the tree. There you go. This puts me at 41 minutes and a half. So almost down. I'm 4 minutes short, but I think it's fine. Do you have any questions? Yeah, sure.
Yeah. So here you made an example of a Merkle tree, which is like static, right? You cannot add another leaves to it.
Yeah.
Are there any, maybe some Merkle, any other tree which is dynamic? Because here you
yes.
have to know the maximum number of leaves. Right?
Yes, I think you always have to know the maximum number of leaves. There are tricks, but the thing you'll notice, right, is that if you want to give yourself a lot of margin, you want to pick a large depth, it grows quickly. It like grows very fast, right? So for a depth of 30, you're arriving at 40 gigabytes of data or something. But there are tricks that I'm not going to get into because I don't feel, I'm not an author of them. It's somebody developed it at work, which is to store part of the tree as a dense tree, right? So you just store the entire tree. And then each update is like a linked list. So essentially, as I mentioned in the presentation, when you update an item in the tree, all the data contained here is just the path to the top, right? So you could just store this subtree entirely in memory, but then whatever update happens to the right side of the tree, when you want to add things, is just like a linked list of these paths to the top, right? It's not going to be as efficient to update, to like calculate the root of that. And you might run, and you might like want to then have some sort of, I don't know, non-mutable data structure, but it should work. But in general, you should know the size of your tree ahead of time. Okay, any more questions? Oh, and by the way, if you want to take a look at this implementation I mentioned, where you can store a part of the tree densely allocated and then a part of the tree, linked listed, if you would, then you might want to take a look at the Semaphore RS library in the WorldCoin repository, which is the company or project I suppose I work for, and you might want to take a look at the lazy Merkle tree implementation. It's a bit verbose, but once you understand it, it's pretty clear how it works. Okay, any more questions?
Could you expand a bit more on how is Merkle tree related to cryptocurrency and stuff?
Mm-hmm.
Because like it's a bit too abstract to me.
Yeah. For example, so I'm gonna lie a little bit because, for example, in Ethereum, it's for example, in Ethereum, right? You might have these famous smart contracts, and each smart contract has a state, right? It can have values that are local to it, that it can mutate, it can update as the chain progresses, moves forward. In order to like maintain and not, send all of this state every time you do a block update, we only send the data that is needed to perform the update, and then we have the Merkle tree represent the state, right? So like in Ethereum, a variable in a smart contract can be thought of as a leaf in the Merkle tree, right? So, and it's usually if you name it something like, I don't know, my variable, then you'll hash the name my variable. Sorry, not hash the name of my variable. It's based on it's like in C++, right? It's based in the order of definition. So you'll hash the number, which is index of it in the smart contract, and that will be your storage slot, right, in the Merkle tree. So you'll update that. That gives you the Merkle tree update. You only send the Merkle tree update every time a block progresses. So that's one example. Now I said I did lie a little bit because I think in practice it's not really a Merkle tree. It's something called a Patricia Merkle tree, which is another level of black magic that I don't want to get into because I don't understand it. Yeah, yet. Any more questions? Yeah.
Can you explain how the Merkle tree helps with the Git deltas?
Not really. I only skimmed over the article to have something to put in the presentation. But my understanding of it, very roughly, right, is that you'll get, like, if you have like 10 files, right, each file is a leaf in the Merkle tree. So when Git communicates with a server on the other side to verify that you have the correct version of a file, it only sends the inclusion proof. But I didn't verify this, so this might not be true, but it kind of checks out, like it makes sense. And that way you only know, when you actually do a pull, you only need to download what is necessary to be up to date with the current version. All right, anything else? Which puts us at 47 minutes, which is, I've overextended my welcome. However, I want to say one more thing, which is that if you think this is cool or interesting or something, we're hiring. So if you're looking for a job and want to try something new, like for example, blockchain, feel free to reach out to me. I didn't put any handles in my presentation, just after this talk, And I thank you for your attention. Thank you for the time. I hope you enjoyed this. Okay. To co teraz? Przerwa? Czy zostawić?
Możesz nas zostawić. Okay, so let's enjoy the break. There will be some snacks, I guess, or yeah. So there will be pizza for everybody here and for everybody online. Enjoy our splash screen for a while. and then we will meet again for a second talk. Thank you very much, Jakub, for explanation on Merkle Trees. Very interesting indeed.